Assalamualaikum and welcome back. This is lecture number 26, and we will look at some concept problem, and also we will solve some sample problem from the book. So let's start. Now, uh, this problem, we have a cantilever beam with a distributed load as shown over here. Distributed load of W applying on the cantilever beam, fixed at B. The span of this beam cantilever beam AB is L, and it is the distributed load is from A to B. The whole beam is under distributed load. Okay, now this problem. For this problem, if you want to find reaction, so there will be a reaction force. One reaction force will be here, RB, and there will be a moment as well, a reaction moment MB. And you can find with the static equilibrium condition considered as a rigid body. But for this problem, we don't have to find these reaction A, RB and MB. So what we will do, we will take a section between A and B anywhere. Let's suppose we take a section over here and we draw free body diagram for that section, and we will find internal shear force and bending moment. Now this shear force and bending moment, due to the loading and the type of support, it will be applicable for the whole beam. Now if I draw a free body diagram for that section, so we have distributed load. Okay, and now following the sign convention, so for this section, we downward we will take positive, and the moment will be clockwise direction, we will take positive. Now we will have a distributed load acting on the beam. So we have a distributed load of W, and this distributed load we can convert into a concentrated load, that is W into X. Now the X is taking this dimension or this length of the beam as X. Now once again, if you look at the beam, we're taking section from left to right. So from left to right we take distance as X. Okay. Now if we consider this shear force V, so we can write the sum of forces in X direction, or sorry, in vertical direction is equal to 0. So we can write sigma F is equal to 0, and that will be equal to V plus Wx, and that will be equal to 0, or V is equal to minus Wx. Now if we take point A, that is at A, that is at X is equal to 0, so the shear force V will be equal to 0. Now at B, now that will become X is equal to L, and the shear force will become minus W. Now this shear force, if you look at the expression, it's changing linearly, 0 at A, and it will be maximum at point B. Okay, and this expression is valid for the whole length of the beam for this problem. Oh, uh, for the moment we have sum of moment is equal to 0, and we are taking moment at this point, and that the expression will be m. Counterclockwise direction is a positive, so m plus, because it's the same direction, wx is the force, and this distance, since it's a uniformly distributed load, so this distance will be x by 2. So the distance will be x by 2 is equal to 0. So moment we can write is equal to w x square by 2, and sorry, there will be minus sign as well. Now if you look at this expression at a, so when x is equal to 0, so value of moment will be equal to 0, and at b, when x is equal to L, so moment is minus w L square by 2. Now if you look at this equation of the moment, that is defining for the whole span of beam, and it's a parabolic equation. Means the bending moment will vary. It will be 0 at A, and it will be maximum at B, and the distribution is parabolic. Now, how to draw shear force and bending moment diagram for this problem? So let's see. Now, if we remember that expression for the shear force, we have V is equal to minus Wx, and for the bending moment we have the expression V m is equal to minus Wx square by 2. Now if we consider shear force, so considering that vertical axis as V, and on the horizontal axis we have length of the beam, so this is V, and A point, B point, and the shear force will vary linearly, and this maximum value will be equal to minus WL. And for the bending moment, let me draw over here. So again, bending moment, it will be from A to B, and this variation of bending moment will be parabolic, and it will be something like this, and the maximum value will be minus WL square by 2. So this is shear force and bending moment diagram for the cantilever beam under distributed load. So if we draw it more precisely, so shear force is varying linearly. It will be 0 at A, and it will increase linearly or change linearly with the length of the beam, and maximum will be at B. And similarly, bending moment, again it will be maximum at B, and the value will be 1/2 WL square, and it will be 0 at A. Now, if you compare both of them, figure or shape force and bending moment diagram. So, bending moment distribution will be always one order higher than the shear force. Now, again, if you look at these both expressions, so this is Wx and this is Wx square. So if you look at compare both of them, so bending moment will always one order higher than the shear force. So by looking at the shear force diagram, you can easily estimate how the bending moment will be. Okay, now let's see a sample problem. This is a overhanging beam. If we classify this beam, this is an overhanging beam, and this is beam AD. We have a load of 20 kilonewton acting at A. We have a support at B and D, and there's another load of 40 kilonewton acting at point C. And this is a rectangular beam. The cross section is shown, that is 80 by 250 millimeter. So for timber beam and loading shown, draw the shear and bending moment diagram and determine the maximum normal stress due to bending. So first we will draw shear force and bending moment diagram. Then we will find the value of maximum bending moment, and with the value of maximum bending moment, we will find the maximum normal stress. But before that, we need to find reaction. So we treat this entire beam as a rigid body, and we will find the reaction at B and D. Then we will take a section at a point near support and load application point. We will take a section, for example, as shown over here. So we take a section after A, then we will take section before B, after B, then we take section before C, and after C we will draw free body diagram or force movement diagram, and we will find the internal shear force and bending moment. And using that, we will draw shear force and bending moment. And then apply the elastic flexure formula, that is sigma is equal to mc over I. We will find the maximum normal stress on that part. Okay, now first we will treat as a rigid body, and we will draw free body diagram, and we will find the reaction at B and C. So reaction at B and C, so at B it's 46 kilonewton, and at D, sorry, not C, D, that is 14 kilonewton. Okay, so I hope you can find easily. Now first we will take just section just after A, and we will draw free body diagram. Now, since for this section we are going from left to right, so we will take this distance as x, and it's good to take to write expression of movement in terms of x and then putting the value of x, because we need that expression in chapter 9 to find the deflection of the beam. Okay, now first we are taking section at just after A, section number 1, and we draw free body diagram. So if you look at this V1 plus 20 kilonewton, that will be equal to 0, and V1 will be minus 20 kilonewton. And moment 1 will be at A, it will be 0. So if we write the expression, so Fy sum of forces in y direction is equal to 0, minus 20 kilonewton minus V1. Sorry, this should be plus 20 kilonewton plus V1. There's a typo. So this is basically 20 plus 20 kilonewton and plus V1. that will be equal to 0. So V1 is minus 20 kilonewton, and moment will be 20 kilonewton multiplied by 0, because we are taking just after A, so distance is almost 0. So M1 is equal to 0, means at A, the moment value of moment will be equal to 0. And now second, we will take a section just before B, and we draw free body diagram. So V2, M2 for the section number 2. So if you want to write, so this again, this should be positive, so both should be positive, plus, and this should be plus as well. So both should be plus. So V2 is just before B is 20 minus 20 kilonewton. Now, if I want to write the expression of M2, so I can write M2 plus 20 kilonewton into X, then that will be equal to 0. Now, if X is equal to 0, so we come back to this expression, this value, so moment 1 is equal to 0, and if you put X is equal to 2.5, that is just before this load B over here, just before load B, so that is 2.5 meter distance. So M2 is 50 kilonewton meter. So what does it mean? That moment will change, it will be 0 at A, so that is at A, and it will be changed linearly, and it will be minus 50 kilonewton just before B. Okay, now third section we will take just after load. So just after load, so this distance is almost negligible, so this distance is almost negligible, so we are taking just after B, so as shown over here, just after B, and we draw free body diagram. V downward will be positive, movement this direction will be positive. So now if we write expression for this one, so that is V3 minus 46 plus 20 is equal to 0. Now V3 will become plus 26 kilonewton meter. Whereas there is no change in moment, because this, so since we are taking moment over here, so moment over here, so this distance will be 0 almost, and 46 multiplied by 0 will be 0. So at just after B, my value of moment will be minus 50 kilonewton. Now, if we take a section just before C, so we can write the expression of V, and with that sum of forces in vertical direction should be equal to 0. So V is 26 kilonewton. So if you look at V3 and V4, so the shear force is constant. Similarly, if you look at V1 and V2, the shear force is constant, that is minus 20 kilonewton, minus 20 kilonewton. But between V3 and V4, that is between B and C, the shear force will be constant, that will be 26 kilonewton. Now, for the moment, so this distance will become X. This whole distance I can write as X, and the moment equation will be M4. Now again taking moment over here. Now, so this will be minus 46 kilonewton x minus and plus 20 kilonewton multiplied by x, and this must be equal to 0. Now then if you put x is equal to 2.5 plus 3, that will become 5.5, so that will give you the value of moment, and that is 28 kilo plus 28 kilonewton meter. And if you put x is equal to 3, so then again it must be equal to minus 50 kilonewton meter. And similarly you can write expression for this by taking section just after C, and if you write expression for V, shear force, and this will be a bending moment. So if bending moment is now just after C, it will be again 28 kilonewton meter. There's no change in shear force. But if you take a section just before D, so shear force is minus 14 kilonewton and the bending moment will be equal to 0. Now if you look at the figure of the figure, so there's a pin joint, and at pin joint the moment will be equal to 0 at the end. So this is how you can find shear force and bending moment for this problem. Now in order to draw shear force diagram, if you look at from previous slide, that internal shear force is constant between A and B, and that is 26 kilonewton negative, 20 kilonewton negative. Then from B to C, it is again constant, but it's 26 kilonewton, and from C to D, it's minus 14 kilonewton. And if you remember from previous slide, the bending moment, if you draw bending moment diagram, it's 0 at A, then it will change linearly, and it's minus 50 kilonewton at B, and then it is from minus 50 to 28 kilonewton meter at C, and from C to D it's again change linearly, and it's 0 at D. Okay, so the maximum bending moment is absolute maximum is 50 kilonewton meter, and whereas maximum shear force is 26 kilonewton. Now in order to find the maximum stress, we know the cross section. The cross section is a rectangular cross section, and if you remember, it's a rectangular cross section of 80 by 250 millimeter. So this dimension is 80 millimeter, and this dimension is 50 millimeter. So, and obviously the neutral axis will pass into the center of the section. So we can apply the elastic fracture formula to find the maximum normal stress. So in this case, it's symmetric about neutral axis. So the maximum compressive and tensile will be same. So using the section modulus for the rectangular section, that is S is equal to 1/6 BH square, putting the value, so value of section modulus. So maximum stress will be 50 kilonewton meter divided by 8.33.3 × 10⁻⁶ meter cube, and that is maximum stress is 60 × 10⁶ megapascal, or 60 megapascals. Okay, now let's see another problem. Uh, Now in this case, this is a cantilever beam with a multiple loading. Now, the structure shown is constructed for a W10 by 112 volt steel beam. So cross section is given. If you go at an appendix C, W shaped beam. So you can easily find the section properties on appendix C of your book. So that designated for the designated beam. W10 by 112 volt steel beam. So what we have to do, we have to draw a shear force and bending moment diagram for the beam and the given loading. And part B, we have to determine the normal stress in the section between the section just to the right and left of the point D. So basically, in this problem, we have to find the stresses just before and after this point D. So what will be the stresses, normal stresses after, just before and after this point D, part B. Now, if you look at this, there's an extension over here, and there's a load acting E at E of 10 kilopounds. Now, this load we have to shift at point D, and when we shift it, we will have one moment that will be equal to 10 kilopounds multiplied by 2 feet, or that will be moment at D, and there will be a force acting downward at point D, and that force will be equal to 10 kilopounds. Okay, how to approach this problem? So again, we replace 10 kilopound load with the equivalent force moving control system at T. Find the reaction at B by considering beam as a rigid body. So at this B, we will have forces. We have a force. We have one reaction force and one bending moment. Then we take a section at a point near the support and the load application point, apply equilibrium analysis, resulting free body diagram to determine internal shear force and bending moment. And using that free body diagram and the bending moment, we will draw shear force and bending diagram. And then we will use the elastic flagellum formula, determine the maximum load stress to the left and right of the beam. Okay, now by making a free body diagram, we can find the reaction at B. So reaction at B, for one, there will be one force of 34 kilopound, and the moment will be 318 kilopound fit, and the direction will be in clockwise direction. Okay, now first we will take a section. So it's a distributed load between A and C. So we are taking a section between A and C, first section over here, and we draw free body diagram section. Now, if you look at this, if I want to write what will be the shear force, equilibrium condition for the forces, so I can write V1 plus 3x is equal to 0. So at x is equal to 0, that is point A, the shear force is 0, but x is equal to the distance of 8 feet. If you multiply with the 8, so that will give me the what will the shear force at point C. So means this is valid from A to C. And similarly, if I want to take a moment over this point, and if I write the moment equation, so m1 plus 3x and multiply by x by 2, that is the distance, is equal to 0, and this is the equation for the movement from A to C. X is equal to 0, so means at A point when x is equal to 8 feet, so we are talking at point C. So by considering this section, we will find the moment. So the equation of the moment, if we write it, so m is equal to 1.5 minus 1.5 times x square, and v is simply minus 3x from C to D. So when we are taking section, so let's take a section just before D, and from C to D, this is the free body diagram. From C to D, just before D, and this is sum of forces in y direction is equal to 0, and V is 24 kilopound, and M2 is the expression is 96 minus 24x kilopound feet. So by using, if I want to write the expression for movement for this, it will be simply M2, let me write M2, plus 24 is the force, 24, and the distance is x minus 4 is equal to 0. Okay, and for the last section, let's take a section just after D between B and D. So drawing free body diagram. So expression for V is 34 kilopound, and M I can write 226 minus 34x kilopound. How we obtain? We obtain simply, let's take M3 minus 20 kilopound feet plus 10 kilopound force, and the distance will be x minus 11. This whole distance is x, so I can write x minus 11. And similarly, this is again acting acting counterclockwise direction, so counterclockwise direction will be positive, so plus 24 into x minus 4 is equal to 0. And by solving it, so m will become 26, sorry, m is equal to 226 minus 34x kilopound feet. So if you put, and this is valid from B to D, and this expression is valid from C to D, and whereas this expression is valid from A to C. Now it's better to write in terms of x, because again, for deflection of the beam, we need this movement in terms of x. Now, by putting the value of x, we can draw shear force diagram. It will now, if you look at the distribution, it's a uniformly distributed load from A to C, but if you look at the shear force, it varies linearly. And from C to D, it's a constant because there is no load between C to D, and again there is change in load. So from D to D, there is no load acting on that. Again, it will be constant from D to B. And the bending moment, if you look at the expression for the bending moment from A to C, that was minus 1.5 times x square. So it's a parabolic curve from A to C, it's a parabolic curve. Now if you look at this is parabolic curve. Then it's a straight line between C to D. Just before D, it will be a straight line, and just after D, it will be minus 168 plus 20 kilopound, so that will become minus 148 kilopound fit. And then from this point D to B, it will be again straight line because it is the shear force is constant, so it will be always 1 meter higher bending moment, so it will be a linearly changing. And the maximum bending moment is 318 kilopound fit. So sigma, we have to find what is the stresses just before and after D. So before D, we have a bending moment of 168 kilopound fit, and after D, that is minus 148 kilopound fit. So section modulus, looking at the appendix C for this beam, the section modulus is 126 h cube about x-axis. So sigma m is m by s to the left of the D. So this is in terms of kilopound inch. So we converted fit into inch by multiplying with 12 and divided by 126 inch cube. So maximum, sigma maximum just before D is 16 ksi, and after D is moment 1776 kilopound inch, converting this 148 in kilopound fit into inches divided by 126, that is section modulus. So we have 14.1 Ks. So in order to draw shear force and bending moment diagram, so we have to take a section just before and after the load application point and draw free body diagram for that section, considering the sign convention, and then we can find by applying the static equilibrium condition, we can find the value of internal shear force and bending. And we can use the bending moment to find stresses by applying the elastic flexibility formula. So by this we will finish this lecture. In next lecture we will solve 2 more problems to further clarify the concept and how to draw shear force and bending moment diagram. So thank you very much.